Okay, so in this video, I'm going to look at the Feynman diagrams for our Dirac Scalar Yukawa theory. So our interaction term in our Lagrangian looks like this. And because it has basically two psi fields and then one phi field, that tells us that our vertices for our Feynman diagrams are going to be built out of basically two solid lines, which will represent our psi particles and antiparticles, and a dashed line that represents our phi particles. And then we have all these rules for how to turn our diagrams into actual calculations, but rather than go through them all, I think I'll just start working through the examples and then we'll just come back to them when we need them. So the first thing I want to look at is the problem I did last time, which is two particles scattering off each other. So I start with two particles, and then in the final state, I still have the two particles. So I want to build a structure out of these things that looks like that process. And the way to do that looks like this. So you can see I have one particle coming in, I have another particle coming in, and then one particle leaving, another particle leaving. And then I have a dashed line in the center. So I guess that you say this interaction is kind of mediated by the phi particle. So how do we turn this into an actual number? Basically, so we have all these, that's how you get the structure. How you label all of these branches is, so for incoming psi particles, we're going to give them a u and then assign a spinor and momentum label. So I've done that here, I've called it u, s, p, and then my other incoming psi particle is down here, and I give it r and q for labels. And then for outgoing psi particles, you write u bars instead and give whatever labels you want. So again, these are my two outgoing particles and they have u bars. And basically, what I've surmised from doing this is when you're doing the calculations, you always contract the spinors that are connected by solid lines. So these two spinors are connected by this solid line, so that tells me I'm going to be contracting this u bar with this u, and then similarly down here. And another thing is the charge. So psi's are the go as b, so they're the particles, not the antiparticles. So that means the charge flows in the same direction as the momentum. And so these arrows on the branches are just the charge arrows. And then we also have to give our inner line a momentum label, just kind of a dummy label. And so now what we do is for each vertex, we need a factor of negative I lambda and a 2 pi to the fourth. So I have that here. And then we have an internal line that is a dotted or a dashed line. So it's the phi propagator. So that's why I have that here. And then we have our contractions. So again, I'm just contracting this and this and this and this. So that's there. And then we have delta functions that just enforce conservation of momentum at each of the vertices. So one vertex, I have p flowing in and k flowing in, and then minus, and then p prime flowing out. So that gives me a delta p plus k minus p prime. And then similarly down here, I have q in and k out and q prime out. So I have a q minus k minus q prime. And I can just do this integral because I have these delta functions. I just replace k with p prime minus p. And so that's how I get that term. And I will have another, so there's another Feynman diagram you could have. You could exchange this u bar with this u bar. And that would give you, so that would, you would just end up exchanging r prime with s prime and p prime with q prime. And because they're fermions, you get a minus sign as well. So the other term would just be the same as this term, but with q prime and r prime replaced, or q prime and s prime swapped with s prime and p prime, whatever it is, the replacements, which is what we found before. So we had these two terms, and we found that they had a relative minus sign. So obviously much quicker. So now let's move on to another one. So this one will be so you have a particle and antiparticle, and they collide, annihilate, and they produce two phi particles. So the diagram that represents that process is this. So again, I have an incoming psi particle, so I give it a us, and the momentum is, and the charge arrow is in the same direction as the momentum. And then I have an incoming antiparticle, so I give it a v bar, and the charge arrow is in the opposite direction of momentum. And then for my outgoing particles, I just need to give them, they're not, they're just scalar fields, so I just need momentum labels. So I'll have p prime and q prime outgoing. So from this, I can apply my rules, only this time it's a little different because I have an internal leg that is a solid line. So that will be, I'll have to use the other propagator, the Dirac propagator. And another subtlety is the Dirac-Feynman propagator is an operator. So it has this p dash, p cross, whatever, p slash in it, plus m. So this is a matrix that will act on a spinner. So when I do my contractions, which obviously I can only do one contraction here, I'll be contracting v bar with u. But what I have to do is, so I have my 2 pi and I lambda factors for the two vertices, but I'll have to write my v bar first, and then my propagator, my Dirac-Feynman propagator, acting on the u spinner. And then again, I just have my delta functions, which are the same. I use the same labels, so they're the same as before. And so now you can, again, just do the integral over k, replace k with p prime minus p. And so, yeah, it's not actually any more complicated. It's just a matter of, you have to realize that the propagator is now an operator acting on u. So you're contracting v with this thing acting on u. And once you make the replacement, it just becomes this. I've just written out, I guess you could technically write p prime minus p cross, maybe, if you wanted. But he just writes it out, expands, it's gamma u contracted with this. And yeah, so there's that. And then interestingly, so the other Feynman diagram you could make is to flip your p prime and q prime. But since you're flipping they're bosons, you don't get a minus sign. So you still have a plus sign, you just exchange q prime and p prime, and that's how you get the second term. And then lastly, we have this. It will be particle-antiparticle scattering off each other. So to do that, we just have this kind of thing. We have our incoming psi particle with a u, incoming antiparticle with a v, you have an outgoing psi particle, which is a u bar, and then an outgoing antiparticle, which is a v. And I've given them all labels. And then another internal phi particle label, momentum label. And again, same kind of thing. Get these factors, the scalar field Feynman propagator, and then I just contract. So there's a question of whether you contract, you could contract u bar and u, or v bar with u. So which one do you do? You contract the ones that are connected by solid lines. So these two are connected by solid lines. I'm going to contract these two, and I'm going to contract these two. So I get this, and then again, delta functions. I just forgot to write the propagator here, so I wrote it over here. But it works out easily enough. You get this. And then a slight subtlety is, okay, now you want to find there's another diagram that we need to write down. But if you just tried to flip, let's say you wrote u bar down here and v up here. Well, now you have two things with bars on the same solid line, and two things without bars on the same solid line. So our rules wouldn't make any sense then, because you can't contract something. You can't multiply two column vectors or two row vectors. So the other thing to do is to flop u bar over here and u over here, and then same down here, but then that would just give you the same thing, because you're still contracting the same same spinners. So you need to find the other diagram that will involve contraction of v bar and u bar and v. And the way you do that is basically you shrink this inner leg down. So if you imagine kind of shrinking this down and connecting these two, and then growing another dashed line outwards between, so to form this kind of thing. So I don't know if that made sense, but basically, hopefully you can see what I mean. But the point is, now I have this diagram, and I have my u and v bar connected by solid lines, and a u bar and v connected by solid lines. So I have what I wanted. And from this diagram, it's easy to work out. Same kind of thing. And there will be a minus sign, because obviously all of our particles we're dealing with are the fermions, the Dirac particles. So there is a minus sign relative to the first term. And I don't think which one of these is minus matters so much, because in the end these are amplitudes, so you're going to be taking the magnitude squared. So as long as the amplitude doesn't change, an overall factor of -1 probably doesn't matter. But the relative factor of -1, the fact that this is a positive term and this one is a negative term, will make a difference. So those, I think that's as far as I'll go as far as the Dirac theory goes. I'll just move on to the problems, the third set of problems from Tong's lecture notes, and then I'll see where I go from there.